We just did this example of an exponential Fourier series. We looked at this function, e to the minus x, on this, it's defined on this interval minus pi to pi. We went through all this, calculated the Fourier coefficients, and simplified them to these. Then the Fourier series was this with all those c sub n's, which in our case became this. By the way, in general, these, for the exponential Fourier series anyway, these coefficients are in general complex numbers. In this case, yes, indeed, it was a complex number. Remember, this f of x is not quite the original function. It's this thing. It's what it converges to. And this shows you that relationship. Here's the original function. Here's what it converges to. But if you're only interested in this original interval, they're the same thing. And they always will be, except any possibility where the original function is not continuous. But other than discrete points like that, the Fourier series is the same as the original function. So you could say these coefficients carry the same information as the original function. Which brings us to the idea of the frequency spectrum. Each coefficient had this way to be computed. In terms of the fundamental frequency, it would look like this, which means each coefficient is a function of an integer multiple of the fundamental frequency. This omega here is the fundamental frequency, which is pi over p when we're talking about symmetric intervals. So I could think of the function as being a function of frequency as opposed to being a function of x. You can look at the function in the frequency domain. And since in general these c sub n's are complex numbers, I need two numbers to describe it then. I either need the real part and the imaginary part, or the magnitude and the angle. For my course in this time, we're going to limit ourselves to looking only at the magnitudes of these coefficients. So we just did this example that had b c sub n's. Here was the Fourier coefficient. Kind of looks ugly. It's got a hyperbolic sign or a sinh involved, and it's a complex number. Well, let's compute the magnitudes for the various c sub n's. For one thing, the magnitude of this thing is always 1. Sine pi over pi is a real number, so its magnitude is just its absolute value. And in fact, they're both positive, so it's just sine pi over pi. Now this part, well, the denominator, 1 plus n squared, n is the integer, so that's just always a real number. So its magnitude, it's positive. So its magnitude is just itself. How do I get the magnitude of a complex number? By Pythagorean theorem. It's the distance in the complex plane. So I take the real part squared, add to it the imaginary parts. Don't square the I. Just the rest of it. It's going to be 1 squared plus n squared, square root of that. Anyway, that would simplify it to this. And if I computed what sinh pi over pi is, I get this. Then everything else, all I do is plug in the proper n's. So I have a formula for each c sub n, which would be this. Now I can just plug in whatever the n is. When n is 0, I just get the sine of pi, sinh of pi over pi. And notice it doesn't matter if n is positive or negative, it's the same thing. So c sub n and c sub minus n are always going to have the same magnitudes. When n is plus or minus 1, I get this. Anyway, I have formulas for each of those. Now I can plot them. Remember, so these c sub n's is a function of frequency, but they only have values at discrete frequencies, at integer multiples of the fundamental frequency. Here's n equals 0, here's n equals 1, n equals 2, etc. N equals minus 1, etc. And they each have a magnitude. So I could plot them like this. I could either put arrows up there or little lollipops or something like that. So this horizontal axis is frequency. I can always do it as multiples of the fundamental frequency. And in this case, what was the fundamental frequency? In our case, here, P was pi, so it was just 1. So actually, this is 1 radian per second, this is 2 radians per second, 3 radians per second, etc. So the units on the horizontal axis are units of frequency. And anytime the function is real, and that's the only cases we're going to handle, you're going to get a symmetric spectrum like this. By the way, when you plot it like this, that's called the frequency spectrum. And if your function is real, it's always going to be symmetric about this y-axis, magnitude axis. That's the idea of frequency spectrum. I'll do another whole example end to end, including frequency spectrum, but I think I'll save it for another recording.